Think about a traffic cop standing at a busy crossing. His job is simple. He tells cars when to go and when to stop. He is important, but he does not build the cars. He does not drive them. He just controls the flow. That is exactly what your CPU has become in modern gaming. It stands in the middle and directs things. But the real heavy work, the smart, powerful work of building the image on your screen, that job now belongs to the GPU and its neural shaders. The CPU has become a traffic cop, and RTX neural shaders are running the show. To understand how big this change is, we need to go back to how things used to work. For most of gaming history, the CPU was truly in charge of everything. When you played a game, the CPU did all the thinking. It tracked where players were, simulated the physics, ran the enemy AI, and managed every system in the game at the same time. After doing all that work, it passed instructions to the GPU and told it exactly what to draw on screen. The GPU had one job: draw fast. It was powerful but obedient. It never made its own decisions. It just did whatever the CPU told it to do. This system made perfect sense for a long time. The CPU was the brain, the GPU was the muscle. The brain thought and the muscle worked. Together, they created every game we ever played. As both chips got faster over the years, games kept improving. Better graphics, smoother movement, bigger worlds. All of it came from the same basic setup. Nobody questioned it because it kept working and kept getting better. But then a problem appeared. Players and developers wanted graphics that looked truly real, the kind where light behaves exactly like it does in real life, where shadows fall naturally, where reflections are accurate, where surfaces look genuinely convincing. Achieving this with traditional math-based rendering is extremely hard. Real light is complicated. It bounces off walls, passes through glass, scatters through materials, and creates hundreds of subtle effects. Game. Developers spent years inventing clever tricks to fake realistic lighting without actually calculating it properly. The tricks worked okay, but you could always tell it was not real. The first big change came in 2018 when NVIDIA launched RTX graphics cards with ray tracing. Ray tracing is a method that actually simulates how real light travels and bounces in a scene. Instead of faking lighting with shortcuts, it traces virtual rays of light and calculates exactly how they interact with every surface. The results looked genuinely beautiful. Reflections were accurate, shadows were soft and natural. Rooms looked properly lit for the first time ever in real-time gaming. But there was a big problem. Ray tracing was extremely slow. Even expensive graphics cards struggled to run it smoothly. NVIDIA needed a solution fast, and the solution they came up with changed everything. Instead of making the GPU calculate faster, they used artificial intelligence to do less calculation in the first place. This technology was called DLSS, Deep Learning Supersampling. The idea was simple: render the game at a lower resolution, then use a trained AI to reconstruct a sharp, full-resolution image. The AI had been trained on massive amounts of image data and learned what good quality graphics look like, so it could take a rough, blurry image and fill in the missing detail intelligently. DLSS worked really well. Performance improved a lot, and ray tracing became usable in real games. But more importantly, DLSS proved something new and important. AI could be trusted to decide what pixels appear on your screen. Before DLSS, every pixel came from traditional calculation. After DLSS, some pixels were created by AI. This was a brand new idea, and NVIDIA kept pushing it further. The next step was frame generation, which came with DLSS 3. This went even further than upscaling. Frame generation actually created completely new frames using AI. Not upscaled frames, brand new ones. The AI looked at real rendered frames, understood what was moving and what was happening in the scene, and then generated new in between frames that the GPU had never actually drawn. These AI-created frames were added to the output alongside the real frames, making games look much smoother. The important thing here is that those AI frames were never touched by the CPU. The game never simulated them. The physics never ran for them. The CPU never sent a single instruction about them. They appeared on your screen purely because an AI running on the GPU decided what they should look like. The traffic cop was standing at the intersection as usual, but cars were appearing out of nowhere that the cop had nothing to do with. Then came RTX neural shaders, and this is where the real transformation happened. To understand neural shaders, you first need to know what a regular shader is. A shader is a small program running on the GPU that decides how surfaces look. It figures out the color, brightness, shininess, and texture of every surface in the scene based on the lighting around it. Normal shaders do this using math formulas. If light hits this surface at this angle with this much brightness, run this calculation and get the color. Pure math, running millions of times every single frame. Neural shaders replace those math formulas with a trained AI brain. Instead of calculating how a surface looks, the AI has learned from huge amounts of real-world images how different materials behave in different lighting. When it needs to figure out how something looks, it does not run a formula. It uses what it has learned and produces an answer the smart way. The result is faster, more flexible, and often looks more realistic than traditional math could ever achieve. The real-world benefits are huge. Many visual effects that were too slow and expensive to run in real time are now possible with neural shaders. The soft glow of light passing through human skin. The way fabric looks different depending on the angle you view it from. The complex shimmer of moving water and light. All of these things need very heavy math if done the traditional way. But a small trained AI model can handle them quickly and accurately using special hardware inside RTX, cards called tensor cores. These cores were built specifically to run AI calculations at very high speed, and they are present in every RTX graphics card made today. So what does all of this mean for the CPU? This is the final and most important part of the story. In the old rendering pipeline, the CPU was needed at every single step. It prepared the data, organized the work, and kept the GPU busy the whole time. The GPU was powerful, but it always depended on the CPU to tell it what to do next. Now with AI, living inside the GPU itself, that dependency is mostly gone. The GPU can look at a scene, understand what is in it, and make smart rendering decisions all on its own. It does not need the CPU to explain what things should look like. It already knows. The CPU still has work to do. It runs the game simulation, handles the physics, manages the sound, and processes player inputs. These are real and important jobs, but when it comes to the actual job of making the image you see on screen, the CPU has been pushed to the side. It hands off the basic scene information and steps back. After that, the GPU and its AI systems take complete control. This is exactly why the traffic cop comparison works so well. The CPU is still standing at the intersection. It is still organizing the flow of information and keeping things moving. But the real action, the intelligent and creative work of building beautiful images every frame, is happening in a place the traffic cop cannot follow or control. RTX neural shaders have taken graphics into completely new territory, a place where intelligence matters more than instructions, where AI inference beats raw math calculation, where the GPU is no longer waiting for orders from above. It is making its own decisions now. It is running the show, and every frame on your screen is proof of that.